Okay, so now we're going to move into Newton's second law. So all this stuff that we've done about torque and moments of inertia are going to come to head with Newton's second law as it applies to rotational motion. Well, we've already seen Newton's second law, that is the sum of the forces equals mass times acceleration, or the net force. We've also written it as this: the sum of the forces equals the mass times the acceleration. All right. Now this law also applies in circular motion. Now, the moment of inertia is simply a measure of an object's rotational inertia. It's a measure of the rotational inertia and if you remember, the mass was a measure of the linear inertia. We didn't call it linear inertia, but the mass was a measure of the inertia. So before, when we had mass in the linear frame, now in the rotational frame, we're going to have moment of inertia. So the moment of inertia is very much analogous to the mass that we use for linear motion. And as we've already talked about, the angular acceleration this is the rotational acceleration. We've already talked about that, where as before we had A, it has now become alpha. So it shouldn't be a huge step then for you to say that before we had F equals ma, now we're going to have the net torque, the vector quantity, is going to equal not mass times acceleration, but moment of inertia times angular acceleration. And so this is Newton's second law in a rotational frame when we have something moving in a circular path. Now, as we've already said, don't forget that torques in the clockwise direction, I said this, I think, but torques in the clockwise direction are considered negative, and those in the counterclockwise direction are considered positive. So that'll be important in this example. So let's consider a disk, and this disk is allowed to rotate about its central axis, and I just want to know, what is its angular acceleration? I have two forces that are causing it to move in different directions, and it's rotating about this axis. All right. A couple things I want to do here. First of all, if I want to know its angular acceleration, I have to say that the sum of the torques equals I times alpha. Well, let's go ahead and figure out what is the moment of inertia. I don't give a mass here. Let's say that the mass is 1 kilogram. So let's say that the mass of this disk is 1 kilogram and that the radius is 1 meter. And then we look back at our table, flip, back to that table. And for a disk, which is really just a cylinder, here, let's just go back up. If I go back up to this, I look at this table and ask myself, which of these objects is that disk which is spinning? And that disk is the same as a cylinder. It's just a flat cylinder. All right, so that tells me that I equals 1/2 mr squared, which is 1/2 of 1 kilogram times 1 meter squared. It's 1/2 of 1 times 1, so it's 0.5 kilogram meters squared. That's my moment of inertia. We'll need that in just a bit. Now, I want to find alpha, so I also need to find the sum of the torques. Let's do that over here. The sum of the torques equals torque 1 plus torque 2. Now this is torque 1. It is causing clockwise motion. So torque 1 is positive, whereas torque 2 causes counterclockwise motion, causes that wheel to turn in the clockwise direction rather. Torque 1 is counterclockwise, torque 2 is clockwise. Just reiterate, I think I said it wrong earlier. Torque 1 is counterclockwise. It causes motion in this direction. It causes the wheel to rotate in the counterclockwise direction, which is the positive direction. And torque 2 causes the wheel to rotate in the clockwise direction, which is negative. All right, so now I can just find a value for this. Torque 1 is going to equal to F1 times R. So that's 1 Newton times 1 meter minus torque 2, which is 2 newtons, times 1 meter. Now in both of these, the angle is 90 degrees, and the sine of 90 equals 1. So I don't include the angles there, but I would have a sine theta term if the angle was something other than 90 degrees. And this gives me a net torque of 1 minus 2, which is negative 1 Newton meters. Negative 1 meaning that it is in the clockwise direction. Okay, so now I have the sum of the torques. I can find alpha. It's just the sum of the torques over I. That's going to be negative 1 Newton meters over, what was our I? 0.5 kilogram meter squared. And that's going to give me my angular acceleration, which is going to be negative 2 radians per second squared. So this is my alpha. It is negative, so it's in the clockwise direction. Okay, now given that you know alpha, now we can ask all sorts of questions like we had in the previous chapter for theta and omega. I have this disk now, it's spinning with a certain angular acceleration. I could ask you, for example, what is its angular velocity after a certain amount of time? What is its position, its angular position after a certain amount of time? And now all that jazz. So